All right, AP Bio. So last week we went 3.1 enzymes where we just did a quick overview of what an enzyme is. Told you a little bit about it. We're going to now take it just a little bit deeper. I know I put on there last week that enzymes are catalysts and that they speed up chemical reaction. So that's where 3.2 enzyme catalysis, that's where it takes over. Okay, so whenever you see this word catalysis, just remember that is a process where an enzyme is speeding up a chemical reaction. Now keep in mind some of these chemical reactions, remember we said carbonic anhydrase, it does this. One enzyme can break 10 to the 6th power. It can join water and carbon dioxide to make carbonic acid. That way our body can get rid of it. It happens so fast. Remember, it's not destroyed in the process as well. But since it's a catalyst, it's got to go through this process of catalysis, causing the acceleration of the chemical reaction. We have, and I can't remember off the top of my head, but there's one chemical reaction in our body that if it wasn't for enzymes that we have, it would take 1 trillion years for this to happen. Well, obviously we can't wait for 1 trillion years. And so we have that enzyme that will speed that chemical reaction to it from 1 trillion years. It'll go I think what they said in milliseconds, it'll happen. And remember that enzyme that does that, it's never destroyed, it's never used up, it's free to move and move and move until it's worn out and it can't do any more reactions, right? So enzymes are catalysts, they speed up a chemical reaction. Now they're also very specific, right? Remember, just like that lock and key model. You got your enzyme and the substrate keep in mind, right, this motion is random, and if it hits just right, then that enzyme, if it hits just right, it'll cause the enzyme to squeeze around it, called induced fit, and then it'll either break that substrate or it will take the substrate and add another one to it to make a molecule bigger. Now, as you remember that, keep that in mind. If you ever hear the word metabolism, that's basically all the chemical reactions going on in your body at once. There are some that absorb energy. There are some that release energy. If you feel your neck, you're kind of warm. We're at 98.6. That's a clue to you that we have chemical reactions in our body that are releasing energy, right? So let's start with the first type of reaction that we would find in our body. It's called an anabolic reaction. Now, anabolic, if I say anabolic, probably the first thing that comes to mind is steroids, because we've probably got a few people walking in the hallways that are doing it. They're not really wise people, but anybody that takes anabolic steroids, right, they're doing it to get bigger. So think of that. They're putting themselves together to get bigger. So anabolic reactions, what they do is they join small molecules into bigger ones, right? So they're building up. And so this is always going to require a little energy to start, right? So keep this in mind that it is going to keep a little energy to start. It's called activation energy, but once it's used, the reaction will go. Now, so you're joining small. So if you look at you're looking at this is, you can see here's your substrates coming in. They got to fit exactly in that active site. When they do, you get that induced fit, and then your product is built. Okay, and a synthesis, I'm just going to leave it right there just so you know. So anabolic, you can see that it's actually taking two smaller substrates and creating one bigger product. Now, catabolic reactions break larger molecules into small ones. Now, where these tend to absorb energy, the anabolic ones, these will release energy. Okay? So it breaks large molecules into smaller ones, requires lots of energy to start. Now, you know this term, hydrolysis. Remember, we talked about that. That is water splitting. So this is where the body would, say, break down a protein strand. It'll get into where the amino acids are. It'll add water to it. It'll use the water, and it'll split the protein strand apart, right? So here you got your substrate going into the active sites. You can see since it fits, it gets the induced fit, it breaks them apart. So you can kind of see how they're connected here. If they fit, then it's going to break it apart. And so that's a reaction that would release energy. Okay. Now we've talked about energy a lot. Energy is always required to start any reaction. Okay, so activation energy is needed to start a chemical reaction. Enzymes tend to lower the activation energy, so it doesn't need to be as high. That means it can happen sooner. Now, when you look at, say, like this diagram, and you can copy it, whatever you have, energy consumed, energy released. This is the activation energy required. So if this is a reactant, it's got to gain enough energy where the reaction will take place, and then you can see it goes into the products. In this case, it's releasing energy. So this is the energy required to start it. Once it reaches that, and then the reaction could take place. Now, if I were to say, let me get my black marker. If I have another enzyme, it may, I don't know how to really kind of, if it's an enzyme, it may lower that temperature. Instead of that temperature coming up to here, it may start it here. So you'll get a quicker release of energy. I had it, I thought, drawn out, but I may end up showing you some more here when I actually get back. So remember, it's going to, any enzyme is going to lower this temperature so it will happen quicker. Okay, and so here's your two. This would energy consumed, energy released. I'm sorry, I'm just trying to think. I don't know that. It seems like I'm missing something, but I'm probably just fine. So I'm going to end it right there, guys. So I'll be back, and we'll take over. And if you have any questions about this when I get back, please let me know.